Hello, this presentation is designed to be a duplicate of one I gave on Friday for online students. The reason I'm making this duplicate is because the recording made on Friday um, didn't present the file in correct format, so parts of diagrams were missing. Well, first of all, I want to ask you all the question whether or not you've got a headset so that you can actually hear me well. And the second point was that I wanted to ask you to make sure that occasionally you are able to use your webcam. I mean, one person has actually said their webcam isn't working. Uh, so thirdly, I'm just checking on the quality of communications between wherever you are in the world and with me here in North London. I'm operating on a 110 megabit line, so from my point of view, communication should be reasonably adequate. So we'll dive straight into topic two, and topic two consists of three parts. The first part is the main part of the today's uh, session, and it involves computer architecture. It's very introductory, but it gets a bit tougher later on. So it's important, and I hope you put in a bit of work to come to understand the main features of what I'm talking about. The second part will consider what I describe as small devices. And all I'm doing is to give you a couple of examples of very, very small scale computer devices which are fully fledged computers. I mean, they're capable of doing whatever any computer is capable of doing. And in addition, they may have several sensors integrated into the computer itself, and we'll have a look at some applications. And finally, I'm turning my attention to Python. So it's a very brief discussion, and I'm introducing some relevant terms, and then I spend part of the session, um, uh, discussing the actual Python language. It's a very introductory level. And I hope you've all caught sight of the YouTube video in topic one on how to install uh, the Python interpreter. Very easy to do, shouldn't take you more than about 5 minutes. Let me know if you have any problems. You should be able to install it on a PC or laptop or a Mac machine. So let me know, keep me informed. And somewhere along the line, I shall actually give you my email address. It's very simple. It's kindberg at outlook.com, and you can always reach me using that email address. So here we go. So topic two concerns computer architecture, and what we're going to do is to examine a simple computer design, and we will analyze its operation. We'll show how this simple uh, arrangement of hardware units can actually uh, uh, produce computations. And we're going to examine what is meant by a program on the way. So here we go. Um, Let me just make sure I can change pages. Yeah, okay, so the architecture of a simple computer is presented, and its typical operation is discussed and analysed. And it's very, I should have said it's very important, so I've got a missing word. It's very important that at the end of this session, you will understand what's meant by the fetch, decode, execute instruction cycle. And cutting a long story short, at the outset, we're thinking about the computer being able to fetch the next instruction to be executed from memory, then bringing it back to a hardware unit, which can actually determine which particular instruction is at issue, and then go ahead and execute it. Typically, uh, 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 the execution will involve the use of the ALU, the arithmetic logic unit. So it's an infinite cycle. Potentially, you're fetching an instruction, uh, looking to see what instruction it is, and then executing it again and again and again. And if the computing device is being driven by a fast clock, say a 3 or 4 gigabyte clock, um, you're going to be able to execute several million instructions per unit time, per second. So everything's happening very, very, very quickly. So, uh, so for most people, a digital computer is simply a black box into which we enter data, and what comes out as a result of putting data into the computer is some result or other that we expect. In the simplest case, we can put two numbers into the computer, and what we will expect as the outcome is the sum or the difference of those two numbers, depending how we've actually programmed the computer. And in general, people don't care how this happens, as long as it does happen. And people are typically concerned about the time it takes to produce results. We want results produced quickly and for those results to be correct. I mean, if I add 4 and 1 together, I don't want to get the result 6. So one of our concerns is going to be how quickly can the computer itself be programmed or reprogrammed? And we're going to say a little bit about what a program is in a moment. So let's just move on a little bit. So in the very early days, and I'm thinking um, in the 1940s or early 50s, a program might have looked like the following. And it's just a very, very long sequence of ones and zeros, nothing else. And maybe you'd find 30 or 40 or 50,000 different symbols, different ones and zeros. And one issue is how do you read this? Can a user just look at a very long sequence of ones and zeros and know immediately what the program does? Or would the programmer actually be able to find faults in the program? Has he made a mistake? How do you know? It's just ones and zeros. And the key idea here is that short sequences of ones and zeros represent two things: instructions and data. And maybe the data occupies uh, lots of ones and zeros because you're dealing with large numbers, for example, or 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 symbols representing other kind of data. And having said that, sometimes ones and zeros can actually represent um, a jump in the program. I mean, it's testing a particular condition. For example, is the contents of memory location Y 1 or a 0? If it's 1, then go to line 10,000. If it's a 0, go to line 500. But we'll have a look at what's called flow of control a bit later on. And it's actually worth saying, I think, that originally a program would actually be represented on paper tape that would be read in to the computer, and the paper tape would consist of little gaps and spaces in the paper that could actually be detected and determined to represent a 1 or a 0. So all that happened quite a long time ago. So what do we actually mean by a program? I mean, we might as well sort of define our terms as we go along. And for our purpose, a program is simply a sequence of instructions which involve both data and operations on data. And an illustration is, okay, well, you're having an operation on the data. Let's take the plus operation. And what data are we referring to? Maybe numerical data. Could be floating point numbers, could be integers. Or the numbers could be very, very large indeed. Or integers less than 100. So generally, some data is not necessarily numerical. I mean, it can be, for example, a tree of symbols, a tree of names, and the operation here might be to traverse the tree and find out what data the tree actually holds. Or data might consist of an array of large numbers, and one operation might be to traverse the array and add each number together. You're accumulating, you want to add each number, an array of numbers, and form a total. So if we look at the program shown above, it actually shows a long sequence of binary numbers. And by binary number, of course, I mean simply a 1 or a 0. A binary number can be either a single binary number, can be either a 1 or a 0. But who could simply tell from looking at these 1s and 0s what the program does or whether there are any errors in it? Very difficult. Or what various sequences or subsequences actually mean. An example of what I'm talking about here is, well, maybe a sequence actually says something to the effect, if a condition X holds, then do operation Y, else, otherwise do operation T. So what we're going to do now is to take a careful look to see what the architecture of a surprisingly simple computer looks like, and how a program such as the one above executes to produce a result. We need to understand that. I mean, you've all heard of Java and perhaps Python, and if you write a program in this high-level language, it's actually going to be translated into the language just involving 1s and 0s. It's a language that a machine understands. It knows what to do with sequences of 1s and 0s. So, the components of a computer, what are they? Well, it's generally accepted that there are three main components within a computer. First of all, the CPU, which stands for the Central Processing Unit. And of course, some computers have many, many different processor units, so there's no single uh, processing unit. It's called a multiprocessor system. Secondly, a computer will contain at least one block of main memory. And thirdly, there will be something called an input and output controller. And a controller simply manages the hardware that allows data to be input into the computer and manages the hardware which allows data to be output from the computer system. And what I have in mind is a common or garden uh, keyboard that allows you, the user, to type in characters or numbers. And an example of what I mean by the hardware allowing output to be made is a VDU or a screen. A visual representation of a particular shape or representation of characters that you've typed or you're editing and so on. But equally, an input to a computer which is being controlled by the controller, being managed by the controller, might be rapid arrival of data from the internet. And also an example of the output might be sending data onto the internet via what's called a socket. Excuse me. And another example of an output device might be a line of sight high-speed microwave dedicated communications device that is being aimed, it's attached to your laptop and it's actually aimed at a satellite above. So it's slightly more interesting example. So the three components, the CPU, the memory and the IOC, the input-output controller, are interconnected by means of a special group of parallel wires. So the wired connections are called buses. And you might say, well, why on earth are they called buses? What's it got to do with a real bus? In London we have red buses and double-decker buses. What's that got to do with parallel wires? Well, it comes from the Latin omnibus, and the idea is that an omnibus can actually transport a number of people from A to B, and in a similar fashion a bus can transfer or transport a number of bits of data from device A to device B. So there's no real mystery in that. So there are three sorts of bus, three kinds of bus. Each bus has a particular purpose. First of all, there's data buses, and these are used to transport or transfer bits of data from device A to device B, or to distribute data across the whole computer system. The second kind of bus is an address bus, and an address in computer science has got a semi-technical meaning. It simply means a label or an address in memory of a particular item of data, a particular datum. And the idea is that memory's capacity to store data is split up into portions of memory, each of which has a unique address, whatever however you like to think of these addresses. So I could have address A and address B and address C. And address A might be represented by a 64-bit number if it's a fairly significantly large memory. But we'll go into that in a little bit more detail fairly soon. And thirdly, um, there are control buses, and control buses are special in the sense that they allow the controller to send control signals to other pieces of hardware in a computer system. I mean, you might want to send a control signal to device A to make it do something, and then quickly afterwards you might want to send another control signal to device B to make it do something else. And thirdly, you might want to send a signal to device C to make it do something. And so having made A, then B, then C perform, maybe you're achieving some overall task. And I'll give you some examples of that happening later on. So data buses allow data to flow from one of the three components to one or more of the others. Control buses enable the three components to be controlled, and maybe subcomponents within those components to be controlled, to enable them to perform their functions as and when needed. So here is a top-level view, or an abstract view of a computer, and I want to give you a little bit more detail of the CPU unit. So this is the CPU, Central Processor Unit. Here's a keyboard, so that's an input device, hardware, screen, output device. Here's the IOC, the input-output controller, and it can send signals and move data to the screen, and the IOC can read data in from the keyboard and take care of it and do what's appropriate with the data that it's received. And here are the three buses: the control, the data, and the other bus. Sorry, I've completely gone out of my mind. Three buses, three buses, three buses. So you've got interconnection between the IOC and the CPU, CPU and the memory and the input-output controller. So if you think of this, these buses as being data or control highways, then I can pull in data from the keyboard, and the input-output controller might decide to store the data in memory for safekeeping. Or it might pull a chunk of data from memory which represents an image, and it's going to be capable of transferring the data on the data bus to the screen, and the screen's hardware is going to allow pixels to receive particular colours, and therefore you get shape and maybe movement on the screen. So just summarising this, three buses are shown here, and remember, a bus is a set of parallel wires. So what are the three buses? There's a control bus, a data bus, and what's the third bus? An address bus. And I'll illustrate the use of address buses, control buses, and data buses in more detail later on. So here's an illustration of an 8-bit bus, and I've got two devices, you choose whatever you want them to be, could be anything, and they're connected by means of a bus, which under a magnifying glass will look like this. You've got 8 parallel wires, And logically, device 1 could send 8 bits of data by putting 1 or a 0 here, 1 or a 0 here, 1 or a 0 here, and the 8 bits of data will be transferred very, very, very quickly indeed to device 2. And I'm sending the data in parallel. I'm sending 8 bits at the same time to device 2. And I'm not implying anything about the direction. I mean, I've spoken as though device 1 can communicate with device 2, but equally, device 2 could use these 8 wires to communicate what's called a word, an 8-bit word, back to device 1. Um, so I guess, the phones you have in your pocket or the laptops that you might have in front of you all contain buses. And maybe the buses on your mobile phone are 128 bits or 64 bits. If you've got an old-fashioned computer, you've probably got 32-bit buses. I mean, the point about having more wires on a data bus means that you can transfer 64-bit numbers or 128-bit numbers internally in the computer extremely quickly. Right, so let's have a look at the CPU. The CPU, Central Processing Unit itself, can be analysed in terms of its two main components. And the first I want to mention is the control unit. So don't confuse the control unit, which I represent usually by CN, the letter CNTL, with the input-output controller. Completely different function. And secondly, the arithmetic logic unit, the ALU. This hardware device is capable of performing very simple operations like add, subtraction, minus, the minus operation, bit shift to the left, maybe bit shift to the right. So each of these components is connected to a register. So what is a register? Let me tell you here and now, and you'll never ever forget it. A register is a small amount of memory. It could be 8 bits worth of memory, or 16 bits, or 32, or 64 bits. It's a relatively very small amount of memory. And the memory is what I'd describe as being very fast to access. To put memory in, it's very quick. The operation to do that is very quick. To get the 64 bits of data out of a 64-bit register, very quick, very fast indeed. So each of these components, the controller and the ALU, is connected to at least one further register. So the controller is connected to what's called the program control register, and I'll explain its purpose in a moment. And the ALU is connected to the accumulator. In other words, the ALU can transfer data into the accumulator and get data back that's been stored in the accumulator. And I'll, as I said, what I can actually do is to tell you straight off what the PC register does. So wait for it and make a note of this. And don't forget what I'm about to tell you. The program control register contains the address in main memory, or the whereabouts, if you like, of the next instruction to be executed. Okay, so any given time in the steady state, the program control register will contain the location of the next instruction that the computer has been programmed to execute. So for the time being, you can view a register as a little bank of memory containing 8, 16, 32 or 64 or 112 bits of storage. A program counter register is connected directly to the control unit, and the accumulator is connected to the ALU. So I'll show you a diagram of this in a moment. The two registers connected, these two registers are connected to two of the three kinds of buses, and we'll discuss the reason for this later on. I mean, the buses are going to be connected directly or indirectly to the data buses because they're holding, the address of a next instruction is, in a sense, data, but typically the program counter will be connected to the address bus, and the accumulator is going to be connected indirectly to a data bus because it's going to receive data from that's output from the ALU or has been transferred from main memory into that particular register for subsequent ALU operations. So three sorts of bus are control, data and address. And what we have as a result of my having just described the ALU is here's the control unit, and it's connected in two ways to the program controller. And if you think of it, the PC is going to contain an address, so it's actually going to be indirectly connected to one of the three buses, in particular the A bus. And you might say, well, why? Because it's the address of the next instruction held in memory. So you can actually put the address onto the address bus, and the controller at a particular point in time is going to say, okay, get the contents of that memory location out and put it onto one of the relevant buses. I want to see what it is. Alright, so what's going to be pulled back is an instruction. And towards the end of this session, I shall actually give you a little bit more detail about the structure of the ALU. Because there's going to be one further register associated with the ALU, and that's called the instruction register, the IR register, and then parts of the jigsaw will all fit into place. So the second component, main component of the ALU is of the CPU is the ALU itself. And that is connected, and these arrows should be bidirectional. The ALU can put data into the accumulator or take it out. Okay, so the whole of this unit is the CPU. This is what a CPU consists of. And here's the memory as before, and we're going to look at what's inside the memory. Right. So before we do that, a little note. After the PC is loaded, its contents are used by the controller to control the operation of much of the rest of the computer hardware. For example, it might instruct the computer to move data into the ALU from memory and then perform a particular ALU operation such as multiplication or plus or minus on the data or the numbers placed or routed into the ALU. So we'll follow that up a bit later on. So the following diagram shows a little bit more detail about how memory itself is split up into two components. And let me explain this. So here we have a device called a decoder. So I've actually missed out the R here. It's a decoder. And alongside it is the memory device, particular memory devices themselves. And this is a row of memory devices, which I'll give you a diagram a bit later on. And each little device is capable of storing a bit of information. So typically, in the simplest possible case, I've got 8 1-bit storage cells and then another row of 8-bit storage cells and so on. And I'm just showing you 8 storage cells here. And maybe the storage cells themselves are capable of storing just 8 bits. And the purpose of the decoder is to select exactly and no more than one of these words. One or more of these 8-bit words stored in memory. So let's just investigate this a little bit. First of all, as a little exercise, supposing you have 8 items and you want to label or name or address each by a unique pattern of bits. Well, if I've got 8 items, I just need 3 bits to be able to uniquely refer to each of those 8 items. Is that okay? Does that seem fair? So 0, 0, 0, so in decimal it's the number 0, can uniquely label the first object, and then 0, 0, 1 in binary, which is 1 in decimal, uniquely can be made to refer to the second item, and the binary number 3, 0, 1, 0, binary number 0, 1, 0, which is 2, can be made to refer uniquely to the third item, and so on and so on. And you get to the 8th bit combination, 111. So that's the 8th bit. In decimal it's 7, binary 111 is the decimal, stands for the decimal number 7. So using just 3 bits, I can refer uniquely to any one of 8 objects. If I wanted to be able to refer uniquely to 16 items, I'd use 4 bits. Okay, so I'd have 0, 0, 0, 0, 0, 0, 0 representing the first item, and I'd use 111, so in decimal that's 15, to represent the 16th item. So I hope that's reasonably clear and straightforward. So these 8 binary numbers will do the job of labeling or naming or what's called addressing the items uniquely. Let's suppose that a very simple memory consists of 8 different 8-bit words, each of which is made up of 8 bits. Right. Suppose that a very simple memory consists of just 8 storage locations, addressable locations, and each word is made up of just 8 bits. Well, we can use what I call electronic addresses, for example 000, 001 as labels to refer to any one of the words in memory. And the role of a decoder is to simply as I said right at the beginning of our discussion on memory, to select any one of these 8 memory locations. The first memory location is 0, 0, 0. The second memory location is 0, 0, 1. The third is 0, 1, 0, and so on, all the way down to 1, 1, 1. So what I need is a little bit of electronics that into which are fed 3 bits on the 3-bit address bus, and this device is going to output a 1, which I can, an active 1, or in terms of voltages, 5 volts plus 5 volts, that will enable me to actually select this row of memory elements. So a decoder has the function of a many-to-one function. Sorry, I'm using the word function twice here. The function, or the purpose of a decoder, is to take a 3-bit number and return a unique number as a result. So I think I've probably made that a bit more complicated than it needs to be. So in a bit more detail, each one of these little squares is connected to an output wire of the decoder. And each one of these little boxes is a single bit storage cell. And what comes in from, I guess, the CPU controller is 8 lines, and each line coming in has the significance of I want to read or to write data to this particular cell, or that particular cell, or that particular cell. This read-write line is indicating that I want to read or write to this column of 1-bit storage cells. So the idea is that supposing I wanted to write a 1 and a 1 and a 1 and a 1 and a 1 8 times here. Well, what I can do is to address put in an address 0, 0, 0, and the decoder is going to output a logic 1 here. And together with, I guess, I need to know what data I'm going to write into it, but I can actually say, well, I'm selecting this row and I'm going to write, so all these lines are going to be logic 1. So I've selected this row. In other words, I'm going to end up writing bits to this row of memory elements. Or if I wanted to read all the bits out of these devices, I could put a 1 and a 1 and a 1 here, which means I've got a 1 coming out here, enabling me to select or focus on these 8 different 1-bit memory cells. And I can develop a little bit of circuitry that enables me to gather all those bits together and put them on the 8-bit data bus, and maybe send them back to memory, or send these bits back to the CPU itself. So I'm just introducing you to a decoder and the idea of 1-bit storage cells and a 3-bit address here. I've introduced you to the function or the purpose of a decoder, selecting any one of these 8 words of memory. And little note here, I think you'll understand that the CPU can put either a 1 or a 0 on each of the 3 wires going into the decoder. Let's supposing 0, 0 is put onto the 3 wires, The job of the decoder is to put a 1 on the first wire, and so on. So I think you'll get the idea. So what does each memory cell look like? Let's have a look. Look at the wires in the diagram again. Each wire coming from the decoder runs left to right, and the wires coming in at the top, and the read-write lines. In other words, these lines can either be 1 or a 0. So if it's a 1, I want to do a read. If it's a 0, I want to write. Run from top to bottom. Right. So if a word is selected by means of a 1 from the decoder, and the words are enabled in order to write data, so for example the read-write line is 1, then data will be captured in that cell. And if it's selected by a 1 from the decoder and each cell is enabled to have data read from it, the data that was stored in the cell will appear on the data bus. And I'm referring to page 18, but I'll supply a little diagram. I don't think I've got a page 18 in this particular document, so I'll let you have that. So don't be alarmed by this diagram. This diagram actually represents I'm going up instead of down. That diagram represents each one of these little devices, these little rectangular devices. So notice the wires coming in from the top. Look at this memory cell hit here. Got a wire coming down and a wire coming across. So the wire coming down is actually this wire here. It's the read-write control signal. This is a separate input, which I haven't shown in the diagram above. I mean, do I want to store a 1 or a 0? This is the input into one of those little rectangles. This line is the select line. So this line actually comes from the decoder. If it's 1, then let's track what effect that has. This is a 1, and a 1 goes in here, and a 1 will go into here. So for those of you that haven't done any modern mathematics or etc. or electronics or anything else, this is the symbol for an AND symbol. And what I've got here is a 3 input AND gate. This is an AND symbol for an AND operation. Only if these 3 inputs are 1, or if you prefer true, will the output be true. So if I've got a single 0 and any one of these inputs, this is going to be a false or a 0. So okay, so select. I'm assuming that the select is 1, because this is the one of the rectangles, one of the single bit memory cells that I want to change the contents on. I want to either read data from it or put a 1 in it. So let's just see what happens. So put a 1 here, that's going to be a 1. And supposing I want this system, this device here in particular, to store a 1. So let me input a 1 here, and the 1 is going to go straight to this AND gate, and it's going to go to this little device here, which is a NOT device, so it's going to invert the value. So a 1 becomes a false. Okay, so I've got a false here, or a 0 here. Got a 1 there, and I've yet to discover what the value of this line into the AND gate is. But it's sufficient to know that this line is false, to know that the output is false. And this line is connected to what's called the R pin. It's the reset pin of this blue device, and I'll explain that in a moment. So let's supposing I want to write data into this device. What I want to do is to write a 1 on the input and store it in this device. So I can't remember which way around about, so I'll have to experiment doing it. A write is going to be a 0. Let the read-write line be a 0. That means I want to do a write. It's a 0. Here's an inverter, so it changes a 0 into a 1, a false into a true, and the true is going to go into this AND gate. So taking stock of all my assumptions, input is 1, fine. Select is 1 because I'm selecting this particular device to make a change in it, to make it store or do something. So I've got a 1 and a 1 and a 1, a true, a true and a true, and the output is true or a 1 here. And this is what's called a set pin. And the definition of the behavior of this very simple device is that if you set it, the output Q is going to become 1. Well, having said that, you'll remember that I've actually got a false here, and it's being attached to the reset pin. If the value on this line had been a 1, the device would have been reset. And what that means is whatever value was being output on the Q pin would be set to a 0. But what's happening in the current situation, I want to write a 1, which is on this line, and I've selected this device to write to. And this is going to be 1 here, and I'm going to set the device. And the definition of setting this device makes Q1. So what else? What else do I need to say? This line was 0, so this input is false, and I get a false here. So I'm not outputting anything, I'm just outputting a 0. But I've succeeded in setting the output, the state of this device to be 1. If I'd reset it, for example, if I put a 0 here, that would have been a 1. And the reset operation would be activated, and Q, the value of Q, would be 0. So what is this blue device that I've been talking about? Well, I'm not going to show you the inside of how it's actually made yet in the course of this the delivery of this topic, but it's called an SR flip-flop, S set reset flip-flop. And the idea of a flip-flop, has just 2 states, 1 or a 0. The output of the device is either 1 or a 0. But okay, just a couple more comments about this particular device. I'm showing it you because of its absolute historical importance. This is an electronic way of building memory. This device can store 1 bit of information. I mean, 100 years ago there was nothing capable of remembering a particular bit of information or a piece of knowledge. First time in history, I think the first flip-flop was probably designed sometime in the 30s or 40s. I mean, I don't know. I'd have to do a little bit of Google research to find out. But I'm showing you this because of its immense importance for the development of digital technology. Without memory, I can do very little electronically of any interest. I mean, you guys have all got memory. You can recall what you did 5 seconds ago, hopefully. Or you can remember what you had for breakfast. And you've got memory. And the an analog of your memory is electronically is this very simple 1-bit device. It's very simple in the sense that it contains just a few logic gates. I mean, in fact, it just contains 5 logic gates, and it's a device that I can decide what to store, and when I want to recall what's stored, I can easily read out the value of Q. Is it a 1? Is it a 0? A little bit of circuitry. 3 inputs. 1, 2, 3, 1 output. And because it's very simple, the size of the electronic construction of a device like this is minute. And I can simply replicate this cell 1,000,000 times or 1,000,000,000 times and end up with a device that's no bigger than something that fits on the palm of your hand. An incredible potential for storing data in a very small space. That is why I'm showing you this. Okay, so I've given you a written explanation of all that, and it'd be great if you can actually look at this particular section, this particular page, and come to grips with it, and just think about it, and consider what I'm claiming here. Just consider it. Memory is critically important to the building of digital computing circuitry. In other words, digital systems. Absolutely crucial. So, still got a bit more to do. And the question is, given the fact that we've got an ALU, we've got a controller, we've got an input-output controller, and we've got memory, how does the whole thing hang together? How does it operate? Well, first need to understand a little bit more about the ALU, and then we'll look at the idea of a computer instruction. What is it? What does it look like? How many are there? What kind of thing can we make a computer do in a moment? So first need to understand more about the ALU. I've already said that the ALU is capable of performing simple arithmetic and logical operations. So amongst the arithmetic operations, it can perform a negation, addition, and possibly, with a bit of programming, some multiplication and division, and so on. If a number is present in the accumulator register and the computer is instructed to add this to a number stored in memory, the results of performing the addition operation will be put into the accumulator. So the scenario is this. typically, somehow or other, we've put a number into the accumulator, and then we tell the ALU to fetch a number stored in main memory and perform the plus operation on the two numbers. The first number being in the accumulator and the new number being freshly arrived at the ALU. And the result will be put into the accumulator. Why is it put into the accumulator? Well, for safekeeping. And maybe all that I wanted to do was to add two very large numbers together. The computer's done it, put the result into the accumulator, and for safety, and I'm going to store it back into main memory. Operation, the program's finished, I've done what I wanted to do, I've now got a result in main memory, which I can look at any time I want to. So questions arising is, how is data input into the ALU, and how is the ALU instructed to perform a given operation on, for example, two numbers? Well, the first part's easy. Each of the two numbers will be stored in memory initially. So from a logical point of view, what's needed is to firstly read memory at a specific address that I've been told, so that each number occupying those locations is put onto the data bus in turn. And the first number is going to be placed into the accumulator, and that's part of the job of the controller, to make sure that that number is going to be put into the accumulator, and that the result of performing an operation on the number in the accumulator and the second number, which has been transported from memory, will be placed in the accumulator. So after memory is read to get the second number, and the ALU is instructed to perform an add operation. So the hardware signal for performing the memory reads and performing the addition will be sent to the ALU via the control bus, and a clock pulse will trigger the operation to be performed. And I'll say more about that a bit later on. So the result of the operation is put into the accumulator by default in case another further operation on that result is required. So for example, if I need to add a number to the number in the accumulator 7 or 8 times, maybe different numbers, I need to accumulate the accumulate the different results of adding further numbers to the number that's already in the accumulator. It's useful to have it in the accumulator. And then I can move the result into main memory at a specific location if I want to. So the symbol for the accumulator looks like this, and the idea is that from memory a number is going to be fetched and put into the accumulator, and that's going to be routed into the ALU, and that's going to be routed into the accumulator register. And then the second number is going to be fetched from memory, and it goes into the ALU, and the control bus says, okay, add this number and the number that's just arrived, and put the result back into the accumulator. So the big question now, and hopefully this is yet another piece of the jigsaw that we need to understand. How is the computer instructed to do all this? Well, the answer is by means of a very simple program using a language that it understands. In other words, a language just consisting of ones and zeros. So the first instruction I'm going to use, and the computer will know what to do with, know how to obey this instruction, is load the data located in address 1 in main memory, and load that number into the accumulator. So it's a very short, simple to read instruction. Just load address 1. Let me give you the meaning again. It's move the number located in address 1 of main memory, move it using the data bus, and put it into the accumulator register. And the second instruction is perform the addition operation on the number that needs to be transported from address 2 in main memory, and bring it back to the accumulator and perform the operation. Add the number to the number that's already in the accumulator to the number to be found in memory location address 2. So that's not too bad. So 2 simple instructions, and these are called, just for your benefit, this kind of instruction are called assembly instructions. Assembly. For some reason they're called assembly instructions. Very simple. And they will actually be stored as ones and zeros in main memory, as we'll see in a moment. So where's this program kept? It's a perfectly good question. Well, the answer is in memory. Do you remember the program counter is a register that stores the address of the next instruction to be executed. It's the address of the next instruction to be executed. Alright, so each instruction will be stored in memory in the form of ones and zeros, and each instruction might be 16 or might be 8 bits long. Depends on the computer you're designing. But the data used by the program, all the numbers that are being referred to in some of the instructions, are going to be stored there too. So for example, I can store 3 instructions, first at location n, second at location n plus 1, and the third at location n plus 3. This instruction might be store address 56. In other words, what does that mean? It means move the number stored at main memory location 56, which might be here, this might be location 56, into the accumulator. And the instruction stored at location n plus 1 might be the instruction of add to the number stored in the accumulator the number stored at location 100, or maybe location 100 is just here in main memory. It's just this little bit here. Okay, so the key what this little diagram shows is the idea that you can store instructions and the data used by the instructions in main memory. So the key idea here is that the program counter will always keep track of the location of the next instruction to be executed. So supposing the computer is actually executing in the instruction that says store the number at location 56. The program counter is going to be immediately updated by the successor of the address of the last location. So if the last location was address 1, the new location of the next instruction to be executed will be A plus 1. Right, so this is important. This little section is important. The computer itself is hardwired to do the following. Fetch the instruction whose memory address is contained in the program counter. It then increments the program counter by 1 so that it is ready to fetch the next instruction. The controller decodes the instruction and then executes it. And I need to say a little bit more about decoding, and I'll probably say a bit more before the end of this session. It then fetches the next instruction to be found in memory at the location specified by the PC register. So here we've got the idea of fetch, decode, and execute. Fetch, execute repeatedly. So let's just say a little bit more about instruction decoding. Instruction decoding is done by the controller, the CNTL. The first few bits of the instruction, when it gets it from main memory, is known as the opcode. An opcode is a short sequence of ones and zeros that represent the operation to be performed. It encodes what operation the ones and zeros represent, or encodes the operation to be performed. So, for example, the plus operation might be represented by 1111. So, as a result of decoding the instruction, right, so at this point in time, the controller knows what instruction is being referred to. One or more wires will be set to 1. For example, in an add instruction, the decoder will place 1s on the control bus to enable the memory to be read and to send the data contained in memory at that address to the ALU via the data bus. So several steps are involved in bringing about the execution of an instruction. So in addition, the add operation will select a control line on the control bus that results in the ALU performing the operation. Adds the number just read from main memory to the one contained in the accumulator, leaving the result in the accumulator. In short, the controller is actually responsible for a sequence of actions that represents the execution of the instruction. So, in partial conclusion, a small example should impress you on the need to cyclically fetch instructions from memory, then decode them, and then perform the specified operation, which may involve reading data in memory or writing data to memory. One possible operation is to place the results of an operation in memory at a particular location, say for some address called address. This time the controller will put address on the address bus for it to be decoded by the memory decoder, and data will be written into the location specified. So I'm going to finish after considering this very, very simple illustration of the fetch execute cycle. And remember, what I've said is that an instruction is going to be stored in memory as ones and zeros, and any instruction is going to have an initial opcode. The first few bits are going to represent the operation that's intended. So for example, here I've got an opcode of 0, which means halt the computer. In other words, I've finished executing the program, stop everything you're doing. The opcode 2, so in other words it's something like 010, 2 in decimal, and it means store the contents of the accumulator in memory. Save the contents, save whatever's in the accumulator in memory. So the 2 is going to be followed by a memory address, and the instruction 2 followed by a memory address means store the contents of the accumulator in memory. So if you, the opcode 4 means, so that's going to be 100 in binary, load the data into the accumulator. Well, it's going to be load the data at some particular main memory location. So the instruction is going to look like 4 followed by a main memory address. Right? Opcode 6 means add the data at a particular memory address to the number in the accumulator. So 110 followed by a memory address. What that means is add the number found at that memory address to the contents of the accumulator and put the result in the accumulator. And the opcode 1117 in decimal simply means subtract the data from some memory address from the number in the accumulator and put the result back into the accumulator. We need 3 bits to represent these potentially 8 different codes. I could have 8 codes, or 8 opcodes. So please, whatever else you do, have a look at this example and try and follow what's happening. On the left hand side, I've got 1, 2, 3, 4, 5, 6, 7. I've just got 7 memory locations, and ranging from 000 to 007. Okay, so let's ask ourselves a question: what is contained at location 000 in memory? Well, the answer is an instruction, because it starts with the opcode 4 and it refers to a main memory location 005. So let me remind myself what the opcode 4 means. It says load data into the accumulator. Load data into the accumulator. So this means load the data found at main memory location 5 into the accumulator. How? Put it on the bus and make sure it gets there. The controller is going to make sure it gets there. So let's have a look at see what's contained in main memory location 5. Here it is. It's 77. So what I'm going to do is simply put the number 77 into the accumulator. Okay? Let's think about executing the next instruction, or whatever that is. Let's have a look at the contents of main memory location 001. Well, we know it's an instruction because it starts off with the opcode 7, so let me remind myself what 7 is. So it's a subtraction of data. What this instruction means: subtract the number to be found in location 7 from the number in the accumulator. Well, we know 77 is already in the accumulator. Let's find out what the number stored at main memory location 7 is. It is, let me just scroll down a little bit. It is 35. 35. So let's subtract 35 from the number found in the accumulator, which, if you will remember, is 77, and put the result into the accumulator. So is it 42? 42 is put into the accumulator. Okay, let's look at what's in main memory location 2. It's this. It's an opcode 2. What's the opcode? What does the opcode 2 stand for? Store the contents of the accumulator in memory. So what this is saying, the 2 means store the location of the accumulator in memory at this location, location 6. Location 6. Okay, we'll do that. Let's have a look at location 6. Well, in fact, it's already got the number 42 in it. So I guess we'll overwrite that number with the result of our subtraction, which is 42. Okay, let's have a look at the next instruction, 003. Remember, this is going to be contained in the program counter. Let's have a look at the opcode 0. Well, I think I can remember that. 0, whoops, right, 0, the opcode 0, let's have a look, the opcode 0 is just stop the computer, you finished. There it is, finish. And we've succeeded in seeing how a simple computer can execute a program. Finish. Okay. So I've given you an explanation, a verbal explanation, instruction by instruction, and I want you to look at that. And I've made a mistake here because the table I gave you should have looked like this. And the table that we end up with, look, here's the contents of location 06, it's just 42. I think I started off with this table, which had 42 in it. And this table should have changed to this table. So, but as things are, the storage at address 006 has been overwritten. I had 42 here. Well, it's actually been overwritten with 42. Okay. So, little example that I'd like you, a little exercise I'd like you to think about. Calculate what happens if 1 is put on input and on select and on read write. If the flip-flop is currently storing a 0. Tell me what happens. And all you have to do is remember that these are 3 input AND gates, NOT gates, invert the value of 1s and 0s. Alright, okay, we'll finish there. Thank you very much for listening. I hope it's been an efficient way of coming to understand the operation of a simple computer. I've covered a lot of ground here, and you need to go over what I've actually written and have told you. Thank you.